All right, so in my last video, I kind of went through and talked a little bit about the differences between microchips and regular CPUs, and the differences between the new MPLAB X versus the other NPLAB versions, MPLAB 8 and prior, and some of the differences as far as XC32 versus XC16 and XC8. I didn't really get into the details as far as this program goes. So let's kind of start on that. I'm going to go to Customize here, and instead of selecting this starter kit, I'm going to select Simulator. So the simulator is something that Microchip is pretty proud of, I guess I would say. And it is an interesting tool. I'm also going to switch to the newest version, XC32, just because I believe we can without any issues. So, and I'm just going to hit OK there. Now that, as soon as you hit OK, you can see that the cursor is a little bit lagged out, and then it's like, yep, you're good to go. So now this is actually set. Those settings are there. It kind of refreshes all your windows. You don't get any details down here that happened, but that's fine. It's I'm just going to clear out this window so you can kind of see. So it took me embarrassingly long time to get this up and running. And the main issues were these setup configurations at the top. So you would think, at least I would think, that there would be defaults here that would allow this to run. So if I said, I'm going to delete all of these and then build it, it will build, I believe. Let's see, it's trying to build. Also, you notice I hit clean and build. So the difference between these two buttons, clean build and just regular build, is the clean deletes some extra files. It'll kind of clean up your project so you don't have any extras, and then build it. One of the things that can happen if you just do build is if the build fails, sometimes you will have files there that you could still load to your microchip, even though the build failed because they're from your last build. So when you do clean, it deletes everything, and you are kind of more certain that it has removed everything that's legacy, I guess you could say, from previous builds. So using the debugger, or the simulator, I'm going to go ahead and start debugging, and that's basically this button right here. So notice that the microchip download upload is not enabled because, well, we don't really have a microchip. We're just simulating that we have a microchip. When we do this, I'm not really sure. It seems like it does build again. Not really exactly sure why, considering we just built it, because it should have all the hex files. The hex file being the actual binary hex code that is getting loaded into the processor itself. That's sort of what you can view as your executable file, basically. But really, I mean, again, because we don't have an operating system on these chips, it's not really an executable file as much as it is sort of like the operating system and everything kind of all merged into one. To sort of explain how that works, if you look at a computer, a standard CPU, Windows, Apple, whatever computer, there's a small chip on the motherboard that is the firmware that does what they call the initial posts. And that is the boot cycle, essentially. So if you have a Dell computer, for example, that's when you see like the Dell screen and maybe some other text, or maybe it's just Dell. You know, a lot of those just have an image that they show. And then once it posts, it actually kicks it over, and that's when you would see like a Windows logo or something like that starting. So that's when it has made the transition from running off of the firmware chip to, and then doing all the initialization for like things like memory, things like figuring out what the CPU is, what frequency we're running at, finding all the drives that you have, what your boot order configuration is, if you're booting from a USB or a CD, DVD, hard drive, if you have multiple hard drives, which hard drive is set. So all that stuff is set in the CMOS, and it really uses that firmware chip, which isn't terribly different from a PIC chip, really, to bootstrap your motherboard and your computer, get everything initialized enough that it can kick it over to Windows and actually start running code. So the way that code starts running essentially is that you have a boot sector on a hard drive or a CD or something like that, and it's a specific spot, really. And I think it's not the very beginning; it's like 1,000 bytes in, I think, or something like that. And that's where the execution starts. And that's where it says, okay, now that we've loaded everything up, we are going to start executing precisely at this bit. And that's your operating system. That's where your operating system starts. And that's where the first thing it's going to do is, show the Windows logo, and then it kind of goes through and starts loading drivers and does all the other things. So it really only, that one kind of transition spot is really only important for that very first time where the handover happens between firmware and your operating system. So that handover essentially, so once you have the operating system running, once that handover happens, Windows has its own places and loops and stuff like that that it handles. So when you're compiling a program for execution on Windows, Windows is controlling all your memory addresses. So you don't say, well, I want to put this at memory address this, and this is because this is the next place it's going to execute. Windows is dynamically controlling all of the memory allocation, and we're talking, obviously way, way, way more memory than we have on a PIC chip. Not, because you've got RAM, and then you've got page files, and, it's gigabytes and gigabytes, of RAM, and, possibly terabytes of essentially storage, EEPROM kind of style storage that you have. So, but on a PIC chip, there is no separate operating system and program. So on Windows, it will actually say, okay, well, you want to run this. This is an executable command. It has certain properties that we understand how to hand off execution from our own thread to this program to allow it to do work. And that's essentially what an executable program in Windows is it allows for a handoff of resources and sort of guiding a thread, possibly a created thread or a CPU thread or whatever. It doesn't, however Windows essentially decides to do it to that program. And that program is then a standalone and runs and obviously can use sort of like we have functions in a program like this, like, it's really lat e set here is actually a function that's embedded in the header files and in the chip, and it's at a certain place actually represented in hardware, in transistors, essentially, and essentially hardwired, basically, I guess you could say, into the actual chip. So with PIC and XC32, you're going to have a lot of things like this that are really, the functions are part of the chip. They're actually hardwired, hard-coded into the chip, versus Windows is all software. So an Intel or AMD processor that's running Windows, it has obviously its own register features and assembly language that actually runs on the chip. But you very infrequently are actually accessing that directly with a, say, C program, in Windows. So it will get compiled to assembly to a certain degree, but Windows still has a very large number of functions that they include to the assembly library for things like, reading from a disk, stuff like that. It's like, yeah, you could probably figure out how to, do that with assembly, but there's assembly instructions that actually deal with those things, and those assembly instructions are actually represented as commands to Windows as opposed to commands to your CPU directly. So sort of like how PIC has functions like, like I said, lat e set, Windows assembly, MASM or whatever, will actually have similar functions that, allow you to do things without having to go all the way down to the hardware, sort of a little bit of an abstraction layer. Basically, and you can actually think of those things largely as drivers. So that's essentially what a driver file is. Like it's a USB driver or a printer driver. It allows you to build your hardware in any way and then have a translation to a more or less standard implementation in a, essentially have like a library file. So printing becomes easier, because you want to be able, like, if you're building a printer, you want to be able to have this printer work with Windows, and you want to be able to create the hardware of the printer however you want, and have it be able to be recognized by Windows, and you to be able to print from any program. Like, I should be able to press Control P, not in this program, but yeah, there you go, Control Alt Shift P. And you can print this code out, and it's got, whatever it is. And this is basically a generic interface to any printer that we have. So it could be an HP printer or an Epson printer or, a Canon printer or, whatever the printer is. As long as the printer driver is installed, that does the translation between Windows and, Windows printer and the printer hardware. So that's sort of what the driver is. So when you're running a program and you're writing a program for Windows, you don't actually have to know how the internals of that printer work. And the reason for that is that you're actually going to be calling the device driver instead. So you're going to be saying that essentially Windows has certain requirements for a printer driver, and these functions are, what it is. Now, obviously, there's a lot more to it as far as the communication protocols that printers use and stuff like that, and what that looks like. And there are some communication protocols that are really kind of specified that the chips support. But essentially, like I said, you're trying to get things to be, you build them to a certain layer so that they're generic. And when you have a generic component, that means it's reusable. So you want your printer or scanner or USB, storage device or whatever to operate in a way that, essentially operates by certain rules, so that operating systems like Windows or Apple or Linux can use those devices without a lot of, I guess, specialty work, right? If that makes sense. So, for example, a USB mass storage device, a thumb drive or a USB drive, depending on what your terminology is for it. There's a very small chip in there, along with some memory that runs, and the interface for these is so generic now that you don't need to have a driver file at all, because each one of these devices acts so much like the next one that the default Windows mass storage device driver actually has the functions to run pretty much all of these. And you can kind of think about that like, the convenience factor is that, what if you plugged in a USB drive and it wasn't recognized? And you're like, what? And they're like, oh yeah, in order to use our USB drives, you have to insert our CD that came with the USB drive and install the driver. You could totally do that. You can literally use a PIC or one of these development boards to create a USB mass storage device that requires a separate Windows driver. You could absolutely do that. You can also, however, create one that doesn't require a separate driver. You can create one that plays by the same rules as all the other USB mass storage devices, and essentially Windows will just recognize and say, oh, okay, well, based on this sort of negotiation protocol and developed protocol that we already have, you tell me in certain ways how large you are. I can query what files you have on you, what your formatting type is, what the block size is that you're formatted to, all that kind of stuff, and through a standard generic interface. So that's one of the things that's really changed a lot in computing in the last, years, say 10 years, is that you used to have to install drivers for a mouse. Now USB mice, same way. It's basically plug and play. Like, if you had to install a driver for a mouse, you'd be like, what? Are you serious? Like, I mean, Very, very infrequently do you have to do that. Same thing for a keyboard, a USB keyboard. If you have a wired USB mouse or a wired USB keyboard, you plug it in and that thing just starts working. And you can plug 10 of them in and it'll just start working. And that's because of the device driver that's running there and the way that those devices interact generically based on a set of rules. So this rule set is the same generally for Windows, for Linux, and for Apple. And that means that you don't have a Apple compatible mouse, you don't have a Windows compatible mouse, you have a more or less agreed upon generic way of interacting with a mouse device on any of these platforms. So it's sort of platform independent. So very good for consumers because that means that you don't have to check and see specifically like what's compatible, what's not. Bluetooth is another example. Like Bluetooth is a very generic type of interface. And for Bluetooth input devices, like for example, a Bluetooth keyboard, you can match that Bluetooth keyboard to a cell phone in a lot of cases, or to a laptop, or to a Bluetooth-enabled desktop. And the interface is the same. So it will allow you to use that keyboard for exactly what you're looking for, you know, based on the fact that, you know, Bluetooth specification of how keyboards should act is very, you know, documented. And as long as your device that you purchased or built works in that function, works in that way, supports those functions, you're essentially good to go. So, so that's sort of the device side of it. Now, again, Windows helps you with all those things because, you know, Windows, Apple, Linux helps you with those things because in the assembly language, you're not directly interfacing with the devices themselves. You're interfacing with the generic drivers. So you don't have to write code that is really quite as specific for Windows programs as you do for PIC programs. For PIC, how you configured an LED or whatever, it is the Wild West, really. You can configure it any way you want. You can have a circuit board printed for a very little amount of money, and you can have one of these PIC chips. Again, it's the Wild West. There is no way in which it's generally defined that you connect these. You can do whatever you want, really, and that's sort of the beauty of the PIC chips as well, is that there is no operating system, there is no device drivers. It's literally as close to the hardware as you can get, using just the bare minimum functions that are included with the chip. So I'm actually want to functions and registers and stuff like that. So in order to figure out what all those are, you really need to look at the XC32 manual, and it's 700 pages long or something like that, and it has all of the functions labeled as far as what this button. It's dense to get into, but it's a great reference. So you can go through a program if you know what compiler it was built for. Again, noting that XC32, XC16, and XC8 are all different, and they have different functions. So if you know this is specifically a 32-bit program, which you wouldn't know just by looking at this, who knows? This could be anything. This structure right here is built for compatibility between all brands, all sizes of chips. So it really kind of loads in whatever. Now, MPLAB X is strong enough and intelligent enough to realize, you know, like for example, that this register right here is set for this this processor. So for the processor that I have specified, this does work. So yeah, maybe I can actually, I don't know how I just did that, but if that was a, yeah, there you go. So you can kind of see that's, so that one's definitely recognized, and you see which bits are set to 0 and which bits are set to 1 for all the tris registers. So, like I said, the real gap here is between Windows, you know, posting and then starting to read at a certain place in RAM or a certain place on the drive in order to boot Windows or something like that, and then handing execution off to an executable, interacting with your mouse and stuff like that through device drivers. That's the Windows side. Windows, Linux, Apple, essentially all the same. On the PIC side, totally different. So what you really have is one hex program that is essentially, you can think about it as your operating system and your program all wrapped up into one. So there is no distinction between the operating system and the program that's running on it. There really is no true operating system because of the fact that these chips are so simple. You're not dealing with any of the things that you really traditionally deal with an operating system, like multi-threading and multiple programs and maybe some reporting functions and things like that. Everything has to be essentially built from scratch. So and that's really a lot of why I have interest in these chips, is because they don't have a lot of stuff included with them. A Raspberry Pi, on the other hand, is essentially a system on a chip. So you are running Linux on that processor. I don't know if anyone has run Windows or if that's even possible to do. Probably possible, but not interesting to me. But anyway, the ARM processors are a system on a chip. They have a lot of other features that they support just flat, straight out of the gate, that really make them operate a lot more like a traditional processor. They require an SD card because they boot in a very similar fashion as a Windows computer. This chip does not boot like that. Now, there's advantages to that. Even the slowest PIC chip, the 57-cent, PIC 10 8-pin chip, is going to go from being powered off to powered on and running in a fraction of a second, versus a Raspberry Pi could take you 5 minutes to get to a screen, or 2 minutes, whatever, to get to an interface screen on Linux. Much different way to interact with things. So the PIC chips are much simpler, but for certain applications, they're much faster. You can think of like your calculator, or like a desk calculator. If you hit the power button and it had to boot for 5 minutes, I mean, that's essentially what a Raspberry Pi would look like in order to get to that kind of level. And the reason is because it has way more capability. There's way more things that are loaded. It's loading an HDMI driver and all these other things. There's no display on a calculator. You can't plug a calculator into HDMI. It's got a small LCD display on it generally. For the lower end calculators, and that's what it has, and that's how it works. So it's limited in scope and what it can do, but it's also extremely fast in what it can do. So that's really the niche that the PIC chips have, and I would say that the niche is kind of getting, the gap between the PIC processors and the ARM processors is getting smaller, because the high-end PIC processors are running at pretty high frequencies. I think there's one that I saw was running at 400 megahertz, versus I believe the first Raspberry Pi was running at about 700 megahertz. And I can tell you for sure that a PIC chip running at 400 megahertz, if you have it programmed correctly, will blow a Raspberry Pi running at 700 megahertz out of the water, for no other reason than the overhead that you have of running an operating system. So when you're running essentially what you could say is close to the metal on a PIC chip, there's not a lot between you and what is actually happening in the silicone on a PIC chip. There is quite a lot between you and the silicone on what's happening on a Raspberry Pi, just because of the way they're built. So much different interface. This video is already getting long, so I'm going to go ahead and stop here and start another one.